All right, welcome everybody to week 15, day 2. Your final textbook reading has just been put out. It is 5 points versus the up to 250 points on the last one. So you guys should do fine. Parallel processing is an important topic. And then I'll go through the appendices and see if there's anything in here. Like GPU stuff is kind of cool. I guess we might do one of those too. All right. So we need to figure out if anybody needs a partner for the code tennis assignment. It looks like only Vacalar is missing a partner right now. If anybody else is missing a partner, has everyone else gotten in contact with their peoples? Anyone else need a partner? No? All right. Then I might have to put together a 3-person group. So I'll be in contact with you, Vacalar. Or you can be my partner. One or the other. Yeah. One or the other. You've messaged twice and no response. Then maybe yeah, let's just do that then. So Dolio and Vacalar, because if he hasn't written back to you, then it's going to be annoying. And so we will put the non-diligent students together and they can ignore each other together. Okay. So the active and diligent students can be partners. So looks like Vacalar and Dolio. Okay. So sorry, whoever was Dolio's partner, you didn't write back. Sucks to be you. All right. And then like the night before, I know I'm going to be getting messages like, wait, I didn't read the homework assignment until now. I have to work for somebody? What? Every time. Okay. So we need to. Did we go over the midterm? Did we go over the midterm? Second midterm? Did we ever like go through the answers on it? I think we did, right? Yeah. Okay. All right. Then we are going to be talking about buses today. Pull up the PowerPoint presentation on that. Buses. All right. And this is kind of the last topic in the class. You're gonna have kind of one more homework assignment. That's going to be making a compiler in assembly, which is kind of fun. Compilers are usually a junior level assignment, but that's because you're making a real compiler, whereas you're going to be making a pretty limited compiler in this class. Oh, where's my coffee? Hang on one second. I'm going to pause. I can't lecture without coffee. What is this? Okay, so we're back. And the lights are on too, which might help. All right. We're going to talk about the Magic School Bus today. Any questions any questions about the homework assignment? So basically, the C++ person, is going to make the arrays and fill them with data. Pass those arrays over to the other person. I think there's an input array and an output array. And so for the output array, you just make an array. Allocate memory for it, or you're going to have a bad time, right? Allocate memory for it, blanket, not blanket, like a blanket, but, blank the memory, set it all to zeros or whatever. And then pass it over to the assembly person. Then the assembly person does something to your array, and you read back the output array, and you try to figure out what they did. Okay? So you're going to make arrays, and you're going to fill it with data. And so the assembly person needs to try to figure out what the C++ person is giving them. So there's going to be a little essay you write. It's just like this much writing. And then you pass it back to the other person, and you say what you did. Like you say, I took all the numbers and multiplied them by 2 or something like that. Try and do something a little more interesting than that, but that's the general idea. Because what we're doing is we're teaching you how to link basically stuff together. And linking is usually simple, it's usually like just this invisible step that takes place after you compile. But as Nick Muya can tell you, last week we ran into a problem with linking because he had two different files that were getting compiled into .o files that were each including a header file, and so they each had a copy of those global functions. And so when we tried combining them into an executable, it's like you have a redefinition, right? There's something called the one definition rule where a function can be defined one time. And so even though it's the exact same function, because it appears in two different .o files, the linker does not know which one is correct. And you might be like, but wait, we've been including, classes all along, and that's been fine. We only need to send the .a file, right? Yes. You're passing an archive to the other person. This is different from how you usually work on GitHub. On GitHub, you usually put up your source code and people will compile the archive file. This is the opposite of that. So if we have a file called header.h, and we're going to make in here class Bob and x and get x and x, and I guess we'll just call this integer. We'll just make it a boxed integer, and integer is a constructor sets x equal to 0. And we're going to have a get x and calm down, coc, void set x new x. X is equal to new x. So we just created a boxed integer type. So it's just a integer in class form. And if we were going to care about this, we would add all the overloads, add, subtract, multiply, divide, modulus, so that our capital I integer class could work like an int, but it's a int that will initialize itself. So this is actually, there's people that have done this. You don't have to do this yourself. There's a book called Safe C++, Tangent to the Tangent. I really like this book. It's not a big book. You'd think it'd be a big book. You'd think it'd be a big book because C++ is reportedly hard to make safe, but you can actually make C++ save fairly easily, and it comes with a bunch of primitive boxed types like this that will initialize themselves and add safety checking features and things like that. So this class is a tangent to a tangent. Yeah, fair enough. Okay, so linking issues though. So we got this, and if we make a file called foo.cc, and hashtag include header.h, Sydney.set x 100, return Sydney.get x. Okay, so what are you not liking here? Cannot call it's easy. All right. Let's see if there's anything else wrong with this. Okay, so we got a function. It makes an integer, sets its private variable. Well, it's not private now. To be 100, and gets it. Whatever. All right. I've learned more cool things about C++ in this class than in CSci40. Yeah, there's a lot of weird corners, but this corner is actually a sharp corner, right? Like, we've talked before about how you can do horrible things like this, like int array 100 cout, for, right? We've talked about this nonsense before. R plus R6, which is perfectly valid C++, because it's base plus offset, right? Yeah, it hurts. Yeah, it should hurt your brain, right? But this is actually a sharp corner, because if you talk to people who do professional C++ programming, a lot of them will tell you about times they had linker error problems, and resolving them can be really annoying. They can be really annoying to resolve. Here, let me show you why. So we're gonna have one .cc file, and we're gonna g++ -c foo.cc, and then we're gonna make a bar.cc, and bar.cc will have a okay. Integer. Okay. And so, what was the other one? Bob. Okay. So if we're going to allow main to call Bob, it needs to know about Bob. And so this is just called a function prototype. And that will allow it to compile. It doesn't allow us to link necessarily. You know, the linker step has to take place. But from the compiler's standpoint, we have promised that a function named Bob exists, takes no parameters, returns an integer. Cool. So now we can do something like this. We would say Pablo.setX and Bob. Right. So it's going to call Bob. The return value of Bob is going to be passed to Pablo, and then we can see out Pablo.getX. All right. Any questions about what this program is doing? I'm just demonstrating. We've got two different .cc files. They're both including a common header file. This should be old hat to you guys. There's nothing new here. Thank you for the blessings. I feel blessed. You can always tell when somebody's an egotist, because they sneeze and they say, "Bless me." Okay. So, finally something I understand. Cool. All right, so Muya says, totally, it's not going to break at all. Why are you so despondent, Muya? This is fine, right? So we do g++ foo.cc bar.cc. Compiles, it links. We run it. Pablo's x has been set to 100. No problem. No problem. Do we need to initiate Pablo? No, there's a constructor on there. And the constructor header.h sets Pablo to be 0. And so we're then setting Pablo's x number variable to be the result of Bob. Bob is this function in another .o file, and it is going to return 100, essentially. Okay, so everything's easy, everything's according to plan. We've got two CC files, including one header file. Works fine. All right, so let's go up here into header.h, or we can partially compile these files if we want. Bar.cc, ++-c foo.cc. And if we look at type the result of that into less. So if we look at all the different things that are available in bar, we see we got main, we got mim copy for some reason, stack check field. Oh, does this have? Yeah. Let's strip this down a little bit. We don't need vector. We don't need algorithm. We don't need the read library. IO stream header. We need. Okay. So if we nm-c bar.o pipe through less, yeah, a lot less stuff in there now. Oh, and actually we could probably alias g++, and then this will turn off address sanitizer. I don't remember if I have address sanitizer on right now. I think maybe I don't. Oh wow. Okay. It's bigger. Strange. So anyhow, so this is the things that are in bar.o. So we've got main, right? Main's our entry point, our function. It's in the text segment. We've got some undefined functions like Bob, right? Because Bob is in a different .cc file, so it's it's been declared but not defined. It's undefined. We've got these guys that are W's that are part of the capital I integer library. And we've got some undefined calls to the output operator. Right? We got cout, and all this stuff is for scouting stuff. And all this stuff is going to get dynamically linked in, right? So, you guys understand this? Like, these things are said to exist in the header file, and then we compile it, and it doesn't actually statically link them. It's actually going to be if I do this without the -c, yeah, well, let's see, LDD bar.o maybe, not okay, G++ foo.o bar.o works fine. LDD get that out. You can see that it will dynamically load the lib standard C++ library, the libc library, the libmath library. These are all the things that get loaded. And that's where it's going to find the missing cout statements. Okay. So if we look at the symbol table for foo, it's even simpler. We've got one function called Bob that is defined in this file. And it's got these calls to integer, because it includes integer also. Now, here's the question. Why does this work? We've got one function here in foo that's defining integer get x. And then if we nm-c bar.o, you can see the same function exists here, right? How does this not violate the one definition rule? Or would you guys like to see what happens when you do violate the one definition rule? Because it is only defined once, true, in one file. But what if we come up here and just make a function called void whatever, and it just returns 420, 690, 42. Actually, is that too big? No, it's fine. All right. So we just made some like nonsense function return. It's not void function. Just made some. Let's call it nonsense. It's always hard coming up with function names when they're just pointless stuff. Name it nice. Okay, nice. All right. So now, if we go through our process again of compiling these things, var.cc, nm-c foo.cc, foo.o, you can see that nice is defined here, right? Because everything in that header file gets copied and pasted into foo. And so we now have Bob defined, we have nice defined in foo. And then if we do the same thing for bar, you'll see that Bob is not defined because it's in that other file, but nice is defined. And so now if we try combining the two, foo.o, bar.o, then it does not work. Multiple definitions of nice, and your code doesn't work. Okay, so how do you know it's undefined? Use undefined, yeah. T means it's in the text segment, I think is what that means. I've never actually bothered looking them up. Yeah, T is in the text section. Yeah. U is undefined. Yeah. And then W is a weak symbol, which is kind of what I want to cover today. So, Let's see if any of these matter. I don't think it matters. Okay. So why did that break? Did you guys see that? Like, if we go back into header.h, this code worked fine. We can include that just fine multiple times. We should probably have a pragma once here. Pragma once. So if we include a file that includes it, and we include it ourselves, we don't get a double include. So pragma once is pretty much needed for all header files, but that wasn't the issue here. What we have is foo including header.h and bar including header.h. It works fine as long as it's in a class, but if it's not in a class, then it explodes. You get a linker error. Okay. Do you guys see what the problem is here? There's something called the one definition rule, right? You cannot have more than one definition in the entire program, and template and types cannot have more than one definition per translation unit. Translation unit's like a file, basically. Okay. So do you see this word here? Non-inline functions. Okay, so zoom in here. So if you try defining a class twice the same way, that violates the ODR, the one definition rule. And this can happen. You're normally not going to do this in a file. But like, let's say you don't have that pragma once, and you double include the same file, right? Like if we come back in here, we just take that out, vim foo.cc. If we do this twice, and normally you're not going to do it twice again, but again, you can include a header that includes the header, and you can include a different header that includes the header, and then all that code would be copied and pasted into your code twice. And this is going to violate the ODR because you now have a redefinition of the class. Okay. That's why it's so important to have pragma once. And you will encounter professors, by the way, that hate this with a burning passion and 1,000 suns. So the more official way, because this is technically not part of the standard, but every compiler does it, or every compiler I've ever used supports it, and it's better than the official way, so I use it. But if you want to do the compiler regards the official way, if not defined, if in def header h, then we hashtag define header h, and then jump down to the bottom of the file and say hashtag endif. And if you forget any of those pieces, then your header guards don't work right. Whereas pragma once is one line of, not code exactly, but it's one line. Okay. So what happens if you make nice inline? Great question. Works fine. Works fine. To look at it now, Bob. Let's see. Bob is defined. All these other things are weak symbols. Okay. Might have to call nice, actually. Let's see here. Because it's being inlined out, probably. Yeah, there's nice. You see that? So nice changed from being a T to a W. And so it changed from being like, this is the actual one time I'm going to define something. Like Bob is defined in one place. One definition could be defined in one place. nice, because it's in a header file, you want it to be not. Because if you put into a header file a function, and that function gets included by different people, and then you try linking those people together, they're each going to have the definition of the header file, of that function in the header file, and it won't link. And so if you make the function inline, then it becomes what's called a weak symbol. And weak symbols can coexist with each other. If you include a weak symbol in multiple header files, then what happens is when you combine them together at the end, it just picks one of them, maybe at random. It's implementation defined. And so if foo.cc has a weak definition of nice and bar.cc has a weak definition of nice, when you combine them, they don't conflict because they're weak definitions. And so the compiler just goes, I'll just use this one. And if they're not the same, then, oh Lord, who knows what's going to happen, right? Like, what if you include two different header files that both have inline function nice, and they're not the same function at all? It could quite literally explode your code. Like I said, linker issues in C++ are really, really nasty. And if you practice safe coding practices, you will generally avoid them. But like I said, a lot of people on major projects have these kinds of issues crop up. And this isn't a hypothetical. This is literally what Moya was going through last week, right? So what does weak mean? Weak means that it is not... so the one definition rule doesn't apply to it, essentially. You can redefine it as many times as you want. It should be the same every time, but you can redefine it as many times as you want. And when the linker comes through to combine them all together, then it just picks one of them. And hopefully they're all the same, so it'll work. Okay? But if you've just made a function like this, it can only be defined in one place. And only one .o file can Bob exists as a T. And all the other ones, if we nm bar.o, sorry. C, you'll see that Bob is undefined, right? And that's how it has to be. So a lot of people can call Bob, but Bob can only be defined in one place. That's indicated by T. It's in the text segment. But you can see all these things with classes, they're automatically inlined. And that's why you were able to have your CC files including classes without having this ever explode on you before. Because classes are all inlined by default. So they're all automatically weak references. And so you can include and use functions and classes, and you've never probably seen this before. But if you ever have a global function in a header file, it gets included in two places. And this also applies to like global variables. Global variables also cause issues. Does that make sense, Trangio? Okay. Cool. All right. Equals negative 42. Right. So if we g++ foo.cc and bar.cc, then linker error. Multiple definition of cool. See that? So if you put a global variable into a header file, you try having everybody include it, then you get multiple redefinition of cool. All right. G++-c foo.cc bar.cc nm-C foo.o. And so cool here is defined. And if we go into bar.o, cool is also defined. And so you have two definitions now of a variable. Okay. So if you want to make a global variable, there's a couple different ways you can do it. Probably the easiest way is to put into a class, right? Header.h, struct cool, static int, cool equals negative 42. Not like that. Must be initialized out of one. Does that work? Okay. So now, if we make a variable of that type named variable name, sorry, so hard. Cool. Okay, so this is making a variable named cool of type cat. Oh my gosh. Whoever's listening to the audio transcript of this is going to be very confused. We've made a variable named cool, C-O-O-L, capital C-O-O-L, of type struct cool with a capital K-O-O-L, who's got a member variable named lowercase barf, K-O-O-L. They're going to throw me out of the ACM for this. Okay. And it's got a constructor also named cool that sets cool equal to 42. Okay, so this is a global. This is a global variable named cool. Will this work? Let's actually, we might not be able to do this either for the exact same reason. It's going to redefine cool. Yeah. Can't do that. All right. RIP. So, but we could do... We could do this void set cool. So you don't like that? What's going on there? Okay. Get cool. Okay. Okay, so that compiles just fine. And so then cc, because it's a class, all right? Global classes are all inlined automatically, so it's fine. So rather than setting Sunny to that, then we could say cool : get cool. And does that work? Called a non-static member function with an object argument. All right. Dereference null pointer. Null pointer points to that. Let's see if that expected. Let's see. I can make this work. Hang on. I'll just make a variable of that type. What's going on here? Okay. So this is calling a static member of a class. Do you guys know what static members are? There's one for the entire class. So every object of this type shares the same variable here. If it's static, all members of that class share it. And that's very useful for doing things like counting how many of you exist. How many copies of cool exist right now. You just increment it every time one is made, and then destructor, you decrement it. There's one static per class. And so you technically don't even need to make an object of it to make this work. I am here, but this isn't actually going to be referring to K at all, right? It's just calling the get cool on the class. And so what can I do to make this really horrible and explode people's brains? Let's see. Null pointer. And we need to cast this to be a cool pointer. And we'll dereference it. Did that work? No. Member reference type null pointer is not a struct. 0. That work? So we're going to cast null to be a cool pointer. Undefined reference to cool. What happened here? Undefined reference to cool. You can make this work because this is technically not actually associated with any object at all, and so I'm literally casting the null pointer to be a cool pointer and then using that to get cool, and it actually doesn't matter because it's not actually associated with the object with the pointer at all. It literally doesn't matter what object we're calling get cool on because it's a static function. And so this is like the one time you can actually dereference a null pointer and nothing happens because it doesn't actually use that memory address for anything. So anyway, yeah, it's. Do you guys see how like horrible this is? Like I can't even begin to explain how horrible this is. We're like we don't want to make a variable of type cool, so we're just gonna convert the null pointer into a cool pointer and then dereference it to access the class's static functions on it. Anyway, the point is that this works, right? And so whenever you do things with classes and things like that, what was they called? It's cool. Nice. And then that works fine. Okay, so the upshot is that if you're making a header file and you need things to be globals, you can make it a class, and this is essentially a global variable that is just wrapped in a class, and so it works fine. Everybody can access it by using that cool : get cool : oh wait, these would have to be static also. Oh, that's why it didn't work. Yeah. Okay. Yeah. All right. But yeah, basically this is just a global that's wrapped in a class, and so that's one way you can make it work. Another way you can do it is to say extern int cool. Extern means sir not appearing in this movie. So let's see. How many up? Fine, I'll just type it myself. .cc bar.cc nm-capital C foo.o. And so okay. Foo.cc. Cool. All right, so cool is undefined. You see that? We're calling a global variable named cool. And I've declared it as an extern. Extern means sir not appearing in this movie. So rather than making a global like that, which would be fine, this would define a variable named cool, and it will cause problems if you ever include it twice, because now you've got two people that both are defining cool. Instead, what you can do is set it to extern. Extern means use external linking, which is extern, there you go, which means use external linking. And then when we look at the symbol table, you can see it is undefined, right? There's a variable named cool, but we just don't know where it is. And if we were to try combining these things together, foo.o, bar.o, then we will have an undefined reference to cool, because cool is not actually defined anywhere. Okay. So we could put it into like bar.cc. So I can have like int cool equals 420 here. And if we g++ -c bar.cc and then dash lowercase c bar.cc nm-capital C bar.o, then you will see that cool is defined here, right? So we have cool defined in one place, and then everybody else who uses the header file would be like, hey, there's this cool dude named Cool who exists somewhere. Do you guys see how that works? So in the header file, we just say, hey, by the way, there's a global named Cool. And if you think this is like some hypothetical, like, oh, Kearney's just talking about weird corners of C++, no, this is literally issues, right? If you want to have a global variable used by multiple files, and when you go off into the real world, you're not going to be coding everything in one file like you do in class. You haven't encountered a lot of these issues simply because, it's rare for us to have 100 files in a homework assignment, right? But what's going to happen is that you're going to have a global or something like that. Globals are generally considered bad, but they still happen for reasons. And so let's say you have a global that's shared among different .cc files. Okay, so you're like, I guess I'll just put it up in the header file. Nope. Multiple violation of the ODR. Okay. I'll put in one file, and then, wait, how do I let other people know this thing exists, And so this is how you do it. You say external linking. This thing exists in some other file. And so you do that, and then in main, it'll be defined in the one place, and then when you link them together, everything's fine. So G++ main dot, it may be important, but it doesn't make it any less weird. Yeah, so, right, so 420 was defined here as 420, and then a different file, it is setting Sydney's X to be cool, and then back in here we get Pablo's. So it's being passed between the different .cc files. Yeah, it is weird, but it's actually like these linker, like, and that's why it's one of the reasons why CSI 45 is so important, is because, until you actually understand how linking works at a certain level, like these issues will just be like, why is it not working? You're like Googling, like, linker errors, and linker errors are not very helpful, like, what the hell does that mean? Multiple definition of cool, you try Googling that on Stack Overflow, and you're like, I don't know what this means, man. This isn't my source code. And that's a temporary file, right, that it made for you. So, trying to hunt those down, like even just trying to understand the error messages is really tricky. And so you need to have kind of a basic competency with linkers. At a really basic level, they're really easy. They just find the different, that function's over there, that function's over there, that function's over there, puts them together into an a.out, done. Dynamic linking, basically the same thing, except rather than bringing it into the executable, it just writes down, this is found in libc over here. And then when you run the program, then it loads that object code from libc. More or less the same thing. But when you start doing things like sharing header files among different .cc files, now you can start running into linker errors. And so, header.h, so if we did inline.org, let's see if this works. Can you do that? Inline variables are only available with monitored C++. Interesting. Interesting. So, recent addition to be able to inline a variable like that. Because, and this is a conversation I had with Nick, which is like, people think the word inline is an optimization thing. Right? Because that's what it originally meant. It's a fair enough observation, is that we think that inline, if you see inline in front of a function, it says, hey, get rid of the function overhead call, right? From taking assembly, you know that there's an overhead every time you call a function. Push registers into memory. Is memory fast? No. At the end of the function, pop. You pop all these things off memory. Is that fast? No. It's not horribly slow, but it's slow, right? So every time you call a function, and if you're calling a function just to do something like this, all those pushes and pops are going to drastically slow down your program, right? And so, if you were smart, if the compiler is smart, it wouldn't do the pushes and pops, but you still are going to have a branch of link, a move of this into R0, probably not even a move. I don't think this would fit. You'd have to do an LDR, which would generate multiple move commands. And then BXLR to jump back out, right? And so that's still, 3 lines of code when it should be 1. You know what I mean? And so it's 3 times slower, even in the best circumstances where you're not pushing and popping registers. Do you guys understand that? And the reason why we inline functions? So rather than calling a function that's small like this, the optimizer will be like, let's just take the body of that function and just put it into the calling function. So rather than having 3 lines of code, we have 1 line of code. It's much faster. And the inline keyword, people think you need to have the inline keyword for it to do that, and the answer is no. The optimizer is free to inline or not inline anything it wants. Just inline everything. It is a hint to the optimizer to inline something, and so it'll be more aggressively inlining things if you put the inline keyword there. But it is free to not inline something. If you have 1,000 lines of code and you put the inline function in front of it, it probably will not inline it. That's one use of inline. The other use of inline is completely unrelated to it, which means it uses weak linking. So, right? It's a completely different, it uses a different linking system, right? That allows you to violate the one definition rule. Classes all use inline linking by default. Like we saw in there, they're all weak, all of these are weak definitions. That's what allows you to use classes without ever having encountered this weird problem before, right? And so Hazelton's like, inline everything? Yeah, if you're making a header file, sure. Why not? We take 4 semesters of CS only, have the optimizer be smarter than you. Yeah, you'd be, I mean, I guess you wouldn't be surprised, Shami, you're a TA, but a lot of CSI 40 students have all these really interesting ideas about how to optimize things, you know, and the reality of the situation is in most of those cases, it's not going to matter. You know, if you combine 2 lines of code into 1 line of code, it's right. Especially after taking this class, you'll understand the assembly generated is going to be the same, right? Whether or not you do like, you know, x is equal to 42, x plus equals to, I don't know, y equals 10. You know, whether those are on 2 lines of code or 1 line of code, it doesn't matter, right? And so they'll do things to like try to optimize their code. Just after you've taken this class and you understand how the optimizer works, it's like, yeah, don't worry about it. Just make your code readable, and then let the optimizer do its magic. And you know, if you have any wasted instructions that don't do anything, those will all get pulled out. Yeah. Top 10 anime betrayals programmer uses inline, optimizer no. Yeah. But the reason why it does that is because sometimes, yeah, you will put inline on a function to use internal leaking or weak, you know, however, inline leaking, however you want to put it. You don't actually want it inlined, right? Like some functions are really, really big. Like there are member functions on classes that are really big. You absolutely do not want them inlined, right? And so the optimizer is used to people using inline to mean weak linking, and so it will not inline it. And it's just a weird artifact of the system that we've got extern for external linking, and we've got inline for internal linking, but inline also means optimize this, I guess. It's just, yeah, it's a weird world we live in. Time to inline all of colors.h. Interesting idea. Oh look, they're all inlined. Yeah, and that's what we did. So see, all of these are inline now. All right. I wonder if like a namespace. Let's see if we can do that. Already got a Bob. Damn it. Namespace. Somebody give me a word. Somebody give me a word. Sus. Cool. All right. So here we could use sus. Cool. And then let's see. still violates ODR. So yeah, a namespace does not make it a weak link. No. Yeah, so namespaces don't do anything. But you could put these into a class if you want. And just, do the static route if you want. Amogus. Okay, so that is a 50-minute long rant about linking. It's like I said, it's one of the more annoying things you'll have to deal with. And the solution was to refactor a header file, which was not, anyone's first choice in the matter. You know what I mean? Okay. And so programs like NM, which, you've probably never seen before this class, they're actually useful for figuring out linker problems. It's sometimes fun to nm a program just to see what function calls it has, things like that. Also, there's a program called strings that I should mention. Strings, they don't know. And that prints out all the strings that are found within the executable. In this case, there's no actual strings, but it's finding all these words from the symbol table. But strings is very useful if you're trying to reverse engineer a program, right? G++.cc. There's no main.cc. What is going on here? All right, G++ hash browns covered and smothered. Run. Okay. So if we type strings a.out, then you will see that there are inside of here. Wow, that's a lot of stuff. There's main. Yeah, right there. So you can see all the different strings that are embedded within the executable, and that's very useful when you're either reverse engineering or you're trying to figure out what the hell is going on with the program. Like there's some executable, and you run it, and it just quits or something. You're like, what, And so running strings on it will see if there's actually things that it's supposed to print, Ooh, what was the ooh for? Reed, do you like strings? It's a cool little program. All right. And the homework. Yeah, you use it with the homework also. So you can do that on the .a file and try and figure out what's happening there. All right. So second half of the lecture today is on the bus. All right. So yep. No fun stuff this year, unfortunately. All right, so get on the bus it's a little goofy. All right. So what is a bus? A bus is a shared transmission line. So if you have Ethernet, you have what's called a point-to-point transmission medium, right? So I've got Ethernet here coming out of my computer, and it's going up to my Eldritch Horror kind of looking router up there, and that's a point-to-point communication. There's not 5 computers attached to that line. However, when I wired my apartment building, and by me I mean like 20 of my closest friends, wired our apartment building for 2 For Ethernet, we used coax. We used coaxial cable. Do you guys know what coax is? I know Hazelton does, probably. You guys know what coax is? Coaxial cable. So coaxial cable is, let's see if we can cut away of it. I guess that works. So you got a copper wire in the center. You got a insulator around the copper wire that's transmitting signal, and you got a ground and like a shielding around it. This is what's used for cable. Like if you have cable TV, the cable that they're talking about in cable television is this. And so back in the day, all television signals were sent wirelessly. We had Wi-Fi. That wasn't Wi-Fi, but right. We originally had Wi-Fi and we switched to wired. And then our internet was originally all wired and switched to mostly Wi-Fi. So I don't know. You tell me about the direction of technological progress. But there was in the 80s a big movement to trench and tunnel and drop these coaxial cables all throughout every neighborhood in the suburbs of America. And so what you do now, if you get a house, is they'll run power, and they'll run telephone, they'll run water, and they'll run coax to your house. If you've ever seen a blank field, like where they're doing development, there's usually going to be this little stand that comes up from it, and it's going to have your utilities for that house. And so coax carries TV, right? But what the cable companies found was in the 90s was that you could send data over it. And so you would have what's called a cable modem attached to this thing, and it would transmit data to the local box, and it would send you data. And you could multiplex it so that you could have both television and data running over the same line. And coax has a fairly good bandwidth, and they've upgraded it, and they've upgraded DOCSIS, which is the protocol they use to talk to it. And so this carries a lot of the home internet in America. It's one of two technologies that delivers internet to our house that is commonly available. Fiber optic, unfortunately, is not commonly available. It's been 25 years, guys. It's time. Come on. The other option for a cable is called twisted cable. And twisted pair. Sorry. Yeah, well, that's what it looks like. Twisted pair cable. And so this is what your phone line looks like. And so there's going to be a series of twisted pairs. These are each copper wires that are twisted around each other. And they're twisted that way, if you've ever taken physics, to eliminate crosstalk. If you have two copper wires parallel to each other, you've got what's called an antenna and a receiver. And so there's going to be huge amounts of interference between the two different wires. But if you put them in a twisted pattern like that, the interference essentially cancels each other out, because when it's on one side, it's pushing the electron voltage. The voltage is pushing electrons one way, and then when the cable's on the other side, it's pushing it the other way, and so it effectively negates itself. And usually these cables will have different numbers of twists, so that there isn't crosstalk between the different pairs of cables as well. And so this is, what your phone looks like if you still have phone service at your house, which I don't think I've ever had phone service at this house. Oh, no, I take it back. I did. My business required a fax machine, of all things. Not because I wanted it, but because when you work with government agencies that are stuck in the 80s and they're like, the only way you're going to send this to us is to fax us. It's like, I guess I'm paying $10 a month for a phone line that I'm not going to use more than 3 times a year. Cool. And I had a fax, but my printer was my fax machine. It was it's the ridiculous thing ever. Yeah, AT&T Internet is using 2 tin cans and a string. Yeah, basically. If you're lucky, it looks like that. So yeah, I did get a good look at my internet cable, Hazelton, because my gardeners, chopped through it 2 weeks ago. And it more or less looks like that. A lot of dirt around here and stuff, but yeah. They came out, they fixed it, and it's all good. So Ethernet is twisted pair as well. But, what we typically call Ethernet is twisted pair, but you can also run Ethernet over coax. And so the reason I'm mentioning all this, coax, is it 2 base? 10 base 2, sorry. 10 base 2. It's been since the 90s since I've messed with this. Yeah, that's what it looked like. Yeah. And so this is a coaxial cable. And we would run it out our window, up 3 stories up the outside of the building, in somebody else's window, and then we would tap it. We'd put a tap onto it. And so the cable would go right on out their window and up another 2 stories and in somebody else's window. There'd be another tap, which would look like that. And then that would be hooked up to like a hub or something like that. And then it would go, you know, in there, and then it would go down 5 stories. And so we had essentially thousands and thousands of feet of this coaxial cable, and everybody was transmitting on it at the same time. It is a shared medium. So basically, all of these taps here are just connecting the conductor here to the cable. It's a single bit of copper that's 2,000 feet long that had 30 different people all connected to it and transmitting it on it at the same time. And so did that work well? No. Did it work? Yes. It did. And because we went from having 100 megabit a second Ethernet in the dorms as a freshman, that's actually why I picked Warren College at UCSD, was because they had 100 megabit a second Ethernet in the dorms, and I'm like, Daddy, you want that bad. And it was a good freshman year, let me tell you. This is a time when people were discovering dial-up, and I had 100 megabit a second Ethernet. I still don't have 100 megabit a second Ethernet now, 25 years later, right? It was a good year. And a lot of people put up file servers and things like that, and we played a lot of games. Then they put us all into the apartments at UCSD's Warren College, which had no high-speed internet at all. And so we just said, all right, fine, I'll just do it myself, like Thanos. And we bought thousands of feet of cabling, and we cabled it together, and it has to be terminated at the end. If you take that off, everything crashes. I was at my work, and we had thin net as well at our work, and I accidentally took the terminator off, and it crashed everyone's machine in the office. And I just heard screaming going up from all around the place as everyone's machines blue screened. And I just looked down at this thing, and I'm like, oh. Just very carefully screw the thing back on. I was like in an unused cubicle. I was like pulling, as an intern techie guy, like you just get tapped to do everything. So I was like pulling cable, and took a quick coffee break. I don't know what happened, man. So that's what that does. Yeah. Yeah. It's not a great system. It is not a great system. Because if any of these things come loose, the entire network goes down. But it's a shared medium, right? And that's what a bus is. Okay? So a bus is a shared transmission medium. To come back to, you thought I was just talking about history. No, I was, but that thin net is a shared transmission medium. It is a single wire that everybody is transmitting on. You can read, you can write to it. And the way that it works with Ethernet, thin net Ethernet, is that if you transmit and nobody else is transmitting, it's fine. You pull the voltage up, you pull the voltage down. All the other Ethernet cards are in receive mode, and so they're just sitting there watching the voltage go like this. And if it wiggles in a certain pattern, they're like, oh, that's me. And then they start recording, like somebody's saying like, hey, bro, here's an email. And all the Ethernet cards are just sitting there watching all the voltages. Like, oh, that's me. And then it'll write it down and put it into the Ethernet card, has like a memory buffer, and then it will send an interrupt to the operating system. The operating system's like, oh, here's some data for us. And the interrupt will pull the data out, and then it puts it into like an internal buffer. And then when the user calls read, then it just reads that data out of the buffer with a system call. And now you guys know how all that stuff works, because you know about system calls now. So in your program, you've got some program that's going to be reading from a socket. A socket's just an integer. You call read on it. And if there's data available to be read, it will copy data out of that internal buffer into your program. There you go. And the operating system gets it from the Ethernet card, and the Ethernet card lets the operating system know it's ready with an interrupt, throws an interrupt. Hey, here's some data. And the rest of the time, it's not bothering anyone. And the Ethernet card is just sitting there watching everything go by. Now, what happens if two people try transmitting at the same time? I try pulling voltage high, you try pulling voltage high. Who wins? And the answer is, when this happens, there's a distinctive burst of electromagnetic noise when two people, or like if one person tries pulling high, one person tries pulling low, you've now got what's called a short circuit, and so it'll detect when two people are trying to transmit at the same time, and this is what they do. They go like this, like, whoa, sorry. And then they each secretly roll a die. 4. Okay, I will wait 4 milliseconds, and then I will transmit again. And the other guy rolls a die. 1. Okay, I'm going to wait 1 millisecond and then transmit again. And so they will randomly wait, and if they just happen to all both roll a 4, then you get this explosion of electromagnetic noise. They both go, whoa, whoa, sorry, and then they roll a bigger die. Okay, I'm going to roll a d20 this time. 16. The other person, 7. Okay, so I wait 7 milliseconds, you wait 12. And it's not milliseconds, I'm just making up numbers here. But they do a random fall-off. But if they both roll a 16 again, all right, time to bust out the D100, and so they do what's called an exponential fall-off, where they wait longer and longer to transmit, because if there's a lot of people all sending and receiving data at the same time, there's going to be a lot of these collisions. And so they will exponentially fall off to allow the common shared media to be clear, because only one person can transmit it on a time. Okay? So, yeah, so if you imagine you have a really long cable and everybody's got an LED attached to it. If you supply voltage, all the LEDs will turn on. But they're not going to turn on that bright because 5 people are drawing power at the same time. And so that's how a bus works inside of your computer. So inside of your computer, you're going to have multiple devices all attached to the same bus. At any one time, one of them is going to be transmitting, one of them is going to be receiving, and the rest of them are probably going to be disconnected from the bus, electromagnetically speaking. Because if you have 5 people all draining power off the bus at the same time, then you try raising the voltage, but that voltage won't go up very much because everybody's sinking the current. And so the devices on the bus will effectively disconnect themselves. Okay. There are serial buses and there are parallel buses. Okay. A serial bus can send 1 bit at a time. A parallel bus can send 8 bits at a time. And you might be like, oh, the parallel bus is faster. And you'd be wrong. Serial buses are actually faster than parallel buses because of the crosstalk between the different wires. And so SATA, serial ATA, right? Universal Serial Bus. Yeah. Have you guys seen SATA? SATA 3G, SATA 6G, whatever. The Universal Serial Bus. There you go. There you go. And so, have you ever, seen solid-state drives? They're almost all SATA drives, right? And so there's 3 gigabits a second, and there's 6 gigabits a second. And these are serial. They transmit 1 bit at a time. And you might be like, oh, why isn't parallel? Wow, no, that's not what I was expecting. Definitely not what I was expecting. All right. Also not what I was expecting. Yeah, so this is not what I was looking for either, but let's do images. There you go. So this is a parallel cable. And so it can transmit multiple bits at the same time, but because people have just tried it, and they were able to get serial faster. So serial connections are, the normal way of doing it now. Okay, so basically if you have everybody reading at once, then the voltage will go down, right? Like imagine you've got, if you guys have taken physics, this will make more sense, but let's say you've got a battery supplying 9 volts, and then you've got 2 devices in parallel that are draining power from it. The voltage drop across them will be 9 volts in both cases, but the amount of current flowing through them is halved. if you have them in serial, then each of them will get half the voltage, but the same amount of current. So no matter how you set it up, you're either going to have less voltage or you're going to have less current flowing through them. And so since these things are usually pretty sensitive to, these are the tolerances for voltages, these are the tolerances for currents, you really don't want to have multiple people reading or writing at the same time. If you do, your bus basically won't work. And the buses will actually try to like shut off bad actors, you know, like if somebody's like screwing up, like according to my professor, when I asked this question, he was like, yeah, the system will try to disconnect it or something. I don't know. But I'm like, but what if the device, or it'll tell the device to turn itself off, I guess he said. And I'm like, follow-up question, what happens if the device doesn't do it? He's like, your system doesn't work, and then you get to tear the thing apart, pulling one card out at a time until you find the bad actor. And then you replace it with a new one. I'm like, cool. My CSI 45 professor was a guy by the name of Muller, actually. I wonder if he's related to Zach, or his brother. And he was, I think, like chief technical officer at NCR. Tempted to say. Mueller. Yeah. Anyway, he was just a lecturer, but he would work full time as like, I think he was chief. I don't know. Maybe I'm promoting him. Maybe I'm demoting him. I don't know. It was a long time ago. But I'm just gonna say he was chief technical officer at NCR. NCR is a company that makes all those like ATMs, and they do a lot of stuff. And so 5 o'clock, you leave his work, you come flying down the road at like 80 miles an hour in his Volvo, come into our class at 5:30, his tie blown over his shoulder, and he would just knock it out of the park. Like the dude was just this amazing professor. He was a real inspiration, and he had real life experience on these kinds of things, you know. So he taught this class because he worked with hardware and software, you know. He knew his stuff. And I like wearing my NCR, the New California Republic. So yeah, so I think they ended up firing him because he didn't really, I think, play politics very well in the department. I don't know. I'm not really sure. But every year there was like this petition to keep him because he was an amazing professor. I think they eventually got rid of him. And about a year or so ago, I was reading about this giant donation that a Blizzard employee made to UCSC's computer science department. Because they're like, yeah, there's this professor called Keith Muller, and he just really inspired me, and that the reason why I'm so successful at Blizzard today is because of him. And I was just laughing because like the department put out this press release saying, oh yeah, he represents everything good about teaching at UCSD, and I'm like, you fired his ass. As far as I know, like I said, I don't have the details on the internal drama, but from what I remember from a long time ago, like they fired him, and then when somebody comes to them with like millions of dollars, like, oh yeah, he was such a good professor. I think that's the I wonder if that's the same one. Lead reliability engineer at BattleNet. Yeah, that's probably the guy. And so he donated money, and they didn't name it after Muller. They named it after Paul Kube. I worked for Kube. He taught CSI 41 and 40. Basically, he was really focused on teaching. I like Kube a lot. Yeah, his deepest interest lay in teaching. Yeah. He retired a few years ago. Okay. Kube said he was speechless when they said the endowed chair would be named his honor. Yeah. So, please consider giving. Yeah, I was just, you know, they didn't name it after Muller, you know, but Kube, I really liked working for him. He was a good guy, so I'm not complaining about that. But Yeah, I was just dying when I read that. But yeah, so anyhow, yeah, that was one of the questions I asked Keith Muller in his class, and like what happens when devices read and write to the bus at the same time, and he's like, it's gonna essentially crash your system. So she walked away all frustrated. That's funny. Yeah, I once had a person. I was in San Francisco of all places. I once had a person tell me I was part of the problem because I was wearing a Shigeru t-shirt. This one. I was walking around San Francisco wearing this t-shirt, and this guy came up to me. He's like, "Do you know how many people that guy has killed?" And I was like, are we talking about like inside of video games or in real life? Because in real life, I'm pretty sure the number is 0, but I could be wrong. I don't know Shigeru Miyamoto that well. And he's like, he's responsible for the death of millions of people. I'm like Koopas maybe, not people. He's like, what do you mean Koopas? I'm like, this is the maker of Mario Brothers, dude. This is not Che. This is not Mao. The maker of Mario Brothers. He's like, oh. Carry on. Make an AI that can teach people computer science. Hell no, dude. I'd be out of a job. All right, so basically, how do you handle this? Like, do you guys understand what I'm getting at here with a shared medium? So, like, let's say that you've got your Ethernet card, and the Ethernet card's trying to talk to RAM, and you've got a sound card. The sound card's trying to talk to the CPU, and they're all transmitting over a shared medium. If you have this, then you've got a problem if everybody's talking at the same time, because the voltages are gonna, right? So there's different ways of solving this problem. You can do something called a crossbar. A crossbar means everybody actually gets their own private channel to everybody else. So if the RAM wants to talk to the CPU, well, RAM, it's not usually on a bus anyway, but if the CPU wants to talk to the sound card, they have its own private line. And if the graphics card wants to talk to the audio card, it's got a private line. It's called a crossbar. It's expensive, but very high performance usually. Another way you can do it is you can have what's called a bus master. And so the bus master is what I was referring to earlier with Keith. And what he said was that you basically have this this guy that runs the bus, he drives the bus. And he says, all right, you can transmit, you receive. And so you transmit, you receive. And, all right, you're done. All right, you transmit, you receive. And it's like a traffic cop, right? Doing this kind of thing. That's Busey contention, totally different. A control bus works by turning on and off your ability to transmit. So it's like I've got a switch over there, and I'm just like, nope, muted. All right, you can talk. You can receive. Okay, turn them off. All right, you can talk. You can receive. Okay. And yeah. Okay. And so a lot of times we'll have different buses, just so that if you're like I said, main memory is usually not on the normal, peripheral bus. It's got its own kind of private channel to the processor, because you really want RAM to go as fast as possible, right? I think you guys should all understand that now. Main memory being able to talk to the cache quickly, good thing, right? It's a very good thing for the cache to be able to talk to main memory quickly. There's a connection between the processor and the cache. And the cache is something, was it the North Bridge or the South Bridge? Which one is that? Yeah, it's a North Bridge, yeah. So the CPU has a North Bridge that connects it to the PCI Express and the RAM. There's a South Bridge that talks to the slower stuff, like USB and older peripherals and things like that. And a lot of times this is integrated into a CPU these days. It's moved into the CPU in modern CPUs. It used to be a separate chip. And the South Bridge, Is that still a separate chip? I think so. Let's see. CPU Southbridge, yeah. And so like if you look at your motherboard and you're wondering what those chips on the motherboard are, like mine has a heat sink on it, right? So if you look down, you can see heat sinks on different weird chips on your motherboard. One of those is probably going to be your Southbridge. And so if you are transmitting data really quickly, it can heat up, and so the heat sink on it will dissipate heat. Do the push. Okay, no, Southbridge I guess is integrated as well. All right. Platform cooler. Directly connected to the CPU via the DMI low power interface. Also integrated on package. Okay. Yeah. So a lot of over time they've been moving more and more of this stuff onto the chip itself. Okay, so yeah. So basically you've got different buses. But the point here is that if you have a bus like this, then only one person can be transmitting and one person can be receiving at a time. And so you've got a memory controller of some sort that will say, SCSI, start transmitting. Video, start receiving. I don't know why you do that, but you could. Or, Ethernet card, start transmitting. Cache, start receiving. And then it'll start feeding data from the network into the cache, right? Do you guys understand this kind of layout? This is kind of an older architecture here. Let's see if I have a different one. Yeah, maybe not. Does this make sense to you guys? And so if you've got really slow things, they might even be another layer away. But basically only one person can be transmitting, one person can be receiving, and you've got some sort of controller that will determine who can transmit and receive at any one time. Okay. Your video card nowadays is going to be attached to the North Bridge, which is a higher bandwidth connection, because you really want good bandwidth between your CPU and your graphics card, right? Because the CPU is going to be setting up your level and stuff like that. Any questions about this? GPU is directly connected to the CPU. Yeah, it depends what you mean by directly connected. It's not. It goes through the PCI Express bus, right? And it's not like there's a cable that runs, between the two of them. So if you ever popped open your machine, and by the way, like if any of you guys are Mac people, it's probably a good idea at some point to actually build your own machine. It's not like you learn that much about computers by building your own machine, but you kind of do. Like you kind of get a better idea of what's going on when you've actually sat down and bought all the parts: motherboard, case, CPU, RAM, cooler, power supply, graphics card, sound card maybe, and actually assemble the machine. And it's a good experience. It's a good rite of passage. I was a Mac person until college, and I was for the first year of college. And then after that, I realized I wanted to play video games and switched to PC and haven't looked back. And I do Linux for all my professional stuff. My PC is a gaming device and video streaming apparently. So, yeah, and so building your own machine is probably a good idea. So yeah, all right. So yeah, it's that North Bridge that we showed you before, right? Which is attached to memory, attached to the CPU. And it is a lane, yeah, so that you can have multiple lanes on a PCI Express device. That's the power adapter. That's an SSD. That's a PCI. No, that's an M2. Yeah. USB card you can stick into your PCI Express bus. That's a 1 times 1. That's a times 16. Graphics cards these days are usually times 16s. They're bigger to get more bandwidth out of them, because that's usually the most demanding part of your computer these days. SSD. So yeah, you can have SSDs plugged into your PCI Express as well. And yeah, so download RTX since chip shortages. Yeah. Oh, I felt very fortunate to get a 3090. One of my students last year told me about the EVGA sign up page where you can sign up to queue up for a video card, and I signed up for it, and then 6 months later it popped, and I got my 3090 at $70 below MSRP, which was the original MSRP, which is nice. If you sign up after April, I think, then they have inflated their prices quite significantly. So that was nice. That was nice. And I'm selling my 2080 Ti right now. So I put it up on eBay. Create a multi-million-dollar mining firm and have NVIDIA sell the chips to you directly. Yeah. Okay. So not through the Northbridge, at least nowadays. Cool. All right. So you've got your RAM, you got your CPU, right? And there's a couple things that actually get transmitted, right? Like if you try loading from memory address 1000, right? So your CPU is going to contact the cache, like, hey, have you ever heard of this memory address 1000 person? The cache is like, no, man, sorry. And then it's going to go out on the system bus here from the Northbridge, and it's going to hit up RAM and be like, hey, RAM, can you tell me what's that memory address 1000? RAM's like, all right, let me work on that. 1000 cycles, 100 cycles, whatever, later, however long it takes, it will come back and be like, hey, on memory address 1000, we found the value 42. Do you guys understand? So there's a memory address and there's a value at the memory address. Yikes. So you're actually sending, there's actually two things you send. There's the memory address and the data. So you've got an address bus. The address bus carries addresses that you're looking to read and write to. And then you've got the data bus that actually carries the data. Do you guys understand? So actually both of these things are going to get sent. If you're on a 32-bit system, there's going to be a 32-bit address bus that says, hey, load memory from this memory address. And then when it returns, it's going to be like, yeah, at this memory address, there's these 32 bits. So you actually have two buses. One for the addressing saying read here, write here. And then you have the actual data that is at those areas. Store to memory address 2000, the value of -6. This is going parallel. And usually they're 32 bits on a 32-bit system. There's always exceptions to these rules. Right? On some older PCs, they'd only hook up like 24 of the 32 bits because they just figured you didn't need any more RAM than that. You know. And then, so you've got the control bus. The control wires control who can transmit, who can receive. The address is the memory address we're going to read or write to. And the data bus controls the actual data being transmitted. So you've got three different buses, essentially, that we call the bus. Yeah. So, yeah. So CPU will read and write to all three of these, and memory will read and write to all three of these, right? And then one bus control them all, and then the darkness fine. Yeah, and then it can go out onto the North Bridge or the South Bridge, and yeah. So now what I said before was that you could have like your graphics card writing to your hard drive. That's nice if you could do that, if the devices support that. So what if, well, let's just say we have a naive system, right? And we're going to be reading a terabyte of data from the graphics card, no, sorry, not the network card. So as this terabyte of data comes in, we come up here, feed it into the processor. The processor's like, yep, that's an 8, all right. And then the processor says, all right, I've read an 8, write it to hard drive. And then it comes back out this way, through the cache, down to this bus, whichever one that is on a modern system, over to here, goes to the SSD. The SSD says, yep, I've written an 8, acknowledge. And then it sends the acknowledgement back over here, it comes up here, comes over here. The CPU's like, all right, it wrote successfully. Let's read another byte from the Ethernet card and comes over here. Let's read another byte. All right, here's your next byte. The next byte is 7. All right, cool. All right, 7's been read. Tell this SSD to write a 7. All right, 7's been written. If it's a hard drive, it's even worse, because if you're writing 1 byte at a time, the hard drive has to seek to that location, and so you're talking 10,000 cycles, 100,000 cycles to write a single character. Comes back up. All right, it's been written. All right, cool. I can move on to the next one now. Try doing that for a terabyte, and you will die of old age, right? And so what would be really nice instead is if the CPU could just be like, hey, network, buddy, go talk to the hard drive. You've got data. He got the space for data. You guys just talk to each other. And then the CPU can sit back here with 0 CPU usage, and your Ethernet card will be reading data as fast as it can from the network, and it will be transmitting it directly to the hard drive, and the hard drive will be writing. Without that, your CPU is going to be pegged, right? If you ever, on some older systems, if you played audio, you would see your CPU usage go up, because your CPU is having to read data off the hard drive and then send that data to the sound card to play. And like, for example, I bought a external sound card in my World of Warcraft days because it improved the frame rate, because the external sound card that I bought could do DMA. It could do direct memory access. And so what was nice about that is that the CPU could just be like, hey, hard drive, talk to the sound card, send the music over. And then the CPU could be free to do other stuff. And so DMA is the notion of one device on a bus can talk directly to another one without having to go through the CPU for every read and write. Okay? Does that make sense to you guys? What the heck is DVD RAM? Is there a DVD RAM on here? DVD. Is that like a rewritable DVD or something like that? Yeah. It's going away. Yeah. So rewritable DVDs. Okay. So yeah, and so you could transmit data, like you could say, hey, hard drive, talk to the DVD RAM, and you know, feed the data over, and the DVD RAM will sit there and burn, you know, will burn it directly, so the CPU doesn't have to be involved. Okay. Casey, do you understand? Rivera? Does DMA make sense to you? Now it's different from TMA. Wait, TMI. DMA is fast, yeah. macOS software that use hard drive space as system memory. And there's just more swap. Then I was wondering why not use DVD RAM. Then I realized I don't know what DB RAM is used for really. Yeah, it's way too slow to be used as RAM. It would be garbage. And in rewriting, it's also pretty slow as well. Yeah, back in the day, it was a good mass storage backup thing. I've still probably got some old data on DVDs somewhere in my closet. I don't think I'm probably going to die before I look at them, but yeah. Nowadays I just use online storage for everything, and it's been working pretty well. Okay. So this I have a worksheet on, so you guys can learn how buses work. Let's see if I have a picture of it. Yeah, okay. So tri-state logic means that in addition to true and false, there is disconnected. Okay, remember how I said that you could disconnect effectively devices from the bus? The bus master, there's different ways of doing this. the bus master can basically disconnect your Ethernet card from the bus. Then it is no longer sourcing current into the bus. It is no longer sinking current and voltage out of the bus. Okay, so you can, if the enable bit is set to false, it goes like this, click, like a switch being turned off. There's no circuit, and so current and voltage will not flow through it. So what you can do with tri-state logic is, let's say that you're trying to transmit, let's see here. Let's say you're trying to transmit a bit, and you've got, where's my mouse? Where's my mouse? You're not plugged in? Are you plugged in? Tablet's not working. Power's on. Power's on, but it's not. Oh, wait. Did I see something? There we go. All right. Weird. All right. So that's again. Okay. So let's say that we've got a hard drive. We've got a SSD. We've got Ethernet, and we've got Wi-Fi. Okay. We call WLAN 0, ETH 0, just to keep it Linuxy. Okay. And we've got two different places that can be writing this data. We've got maybe the hard drive and the SSD. And if you're like, wait, you can read and write to a hard drive? Yeah, that's how they work. So, let's say that we want to have the Ethernet card write directly to the SSD. So what we would do is we would set the enable bit here to be 0. That would disconnect it. We would set the enable bit here to be 1. That would connect it to the bus. This guy's enable bit would be 0, so that's disconnected. And we wanted to, what, read from Ethernet, I said? Yeah. So that enable bit would be true. This enable bit would be false, so that's disconnected. This is connected. And Wi-Fi's enable bit would be set to 0, so that'd be disconnected. And so what you have is effectively a wire running between, and these are diodes that only allow current to flow in one direction. So if this guy transmits 1101, then the SSD will get 1101. Do you guys see that? So the enable bits are literally connecting and disconnecting people to the bus. The bus is just, you can think of it as a piece of copper, right? And so these things are like switches. And so if you switch this on, current will flow from Ethernet 0 through the bus to the SSD. The SSD is in the receive state right now, so it's going to be reading voltages that come in. The Ethernet card is in the transmit state right now, so it's going to be sending voltages out. It's going to be raising voltages up and down, and this guy's going to be reading them. That makes sense to you guys? So it's like you got a set of switches, and exactly one of them could be on. 0010. If two of them are on, then you're in trouble, right? Because it's going to split the current between the two of them. And you don't want two people transmitting at the same time, because then if you have two people transmitting at the same time and this guy transmits high voltage and this guy transmits low voltage, then the current will actually run from high voltage into low voltage and quite possibly explode the device. So if you have two people transmitting at the same time, and by the way, that's why you have a diode there, right? The diode prevents electricity from flowing backwards into it and killing the device. But yeah, they have limitations, and it's quite possible you destroy your device by setting it up wrong. You're not going to see this as a user. This is computer engineering kind of stuff. Singh, Dahlberg, do you guys understand what's going on here by this diagram? You guys know how circuits work? Okay. So let's take a look at... So tri-state logic, there's three possibilities, right? You can have either true, false, or disconnected. Okay. Sometimes called floating, sometimes called high impedance mode. Okay. And so if you have this guy in disconnected, this guy disconnected, this guy transmitting a high voltage, this guy disconnected, and this guy reading a voltage, then he will read a voltage of 1. Okay. And that's how it works. It's one of the ways it works. Okay. So, and then after it's done transmitting, then the bus master will be like, all right, you disconnect, 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 connect, disconnect. All right, you and you talk. And then the hard drive would send data to the hard drive, I guess, or something like that. And so it'll selectively connect and disconnect different devices so they can read and write. And so you can have device A talking to device C, device B talking to device D. That's how these things are set up. This is something called a multiplexer, also known as a MUX. So multiplexer takes as input like in this case 4 different options, and it sends one of them out. It's called a MUX. And a demultiplexer works the other way. So it takes in, it's going to take 2 in this case, so wired 2. So that's also as the input. So you take 4 different inputs, and then a thing that selects which input you want, and it will say, all right, B, number 2 is B, so B comes in. And then you have a demux here, and the demux will take in, this data, and we'll say 1, and then the data will come out here. So it's a multiplexer and a demultiplexer is the terminology for what's going on here. You might not need to know that until you take your electrical engineering classes or computer engineering classes. But that's what the term is. So multiplexer selects from different inputs. So if you got 4 inputs, it selects one of them. And the demultiplexer says for an input, select from the different outputs. Tran, will you? Make sense? Do you understand what I mean by a multiplexer and a demultiplexer? Multiplexer is a bit of silicon that will select from 4 different inputs, give that as output. A demultiplexer takes an input and selects from the different outputs. And so it's like a routing system, kind of. You've seen MUXes on MacBook boards, yeah. Yeah, it's a pretty common term. Yeah. TMUX, right? Yeah, TMUX is a terminal multiplexer, right? So you can have different terminals attached, and then you select which one you have up on your screen. Right? Terminal TMUX. Yeah, very good. Okay. So, yeah, that's what it stands for. Do I have it installed now? There you go. Yeah, TMUX is really cool. I need to learn it better. So you can have a number of terminals, and you can switch back and forth between them. You can actually have a terminal persist. You could disconnect from the server and reconnect and reattach to it and stuff like that. So, yeah. TMUX is one of those things that I really want to spend more time with, because what I want to have actually is when a student connects to the server, it automatically launches TMUX for them. And then if they disconnect, it will save their session, and when they relog in the next time, it'll bring them right back where they were before. Which would work in most circumstances unless they have like an infinite loop or something like that, in which case then they can't even use putty. They can't even kill putty to kill the program. So it's one of those things where I need to like dig into it to to like get, figure out, okay, if there's a runaway process, like how do you, I don't know. It's something I definitely want to spend more time with. Final worksheet for the year. Okay, so it'll be worth as much as your output. Yeah, whatever. Don't worry about that. Right, so if the input control is 1, that means you're attached to the bus. If the input control is 0, that means you're detached from the bus. And so none of your voltage is going to propagate across. So if your input control is 0, it doesn't matter what voltage you have over here. It's sending no data to the bus. Whereas if your input control is 1, then whatever data you have here gets sent to the bus. That makes sense? Let's take a look at that. Okay, so if yeah, just a few questions, not too bad. All right, so do we have? Does this work? Yes. Okay. All right. So for the first question, the input is 0, 0, 1, 0 for the bits are listed in order. Yeah. Okay. So the enable bit is 0. Enable bit is 0. The enable bit is 1. The enable bit is 0. Do you guys see that right here? No, that's the input. Sorry, it's not the control. The input. Okay, so the voltage on this line is 0 volts, 0 volts, high, which could be 1 volt, 3 volts, 5 volts, 9 volts, I don't know. High, 1 means high, 0 volts. So the input is 0, 0, 1, 0. And the control bits are the 6 control bits. So 0, 0, 1, 0, 1, 0. So what is going to be output? Your output is only going to be 2 things. You're going to output the voltage here. You're going to output the voltage here. So what is the voltage going to be on the first bit here? Mr. Lay. Anyone? You weren't paying attention? All right. So let's run through it together. So if we have 0 volts, 0 volts, 5 volts, and 0 volts on these wires, these are just wires coming in, maybe from different devices. The control bits choose whether or not these wires are attached to the bus. In the case of 0, they're not attached. Not attached, not attached. And so this one is 1, so that means there is a connection between this wire and the bus. The bus is now going to be at high 5 volts as well. Now for the output, it's the same thing. 1 means that this copper here is attached to the wire coming out here, and this 0 means it is not attached. So if we got 5 volts here, we got 5 volts here, so we got 5 volts here. So it's a 1. Okay. So the output is going to be high for this one, and it is going to be float for this one. Right? Because the second one is not attached to the bus, its voltage is floating. Okay. Let's do the second one. Input. 1, 1, 1, 1. All of these guys have high voltage. Control 0, 0, 1, 0. It's the same as before, huh? 1, 0. Disconnected, disconnected. This guy's got high coming in, so it's got high coming out. So the bus is going to have high on it. This guy's disconnected. This guy's disconnected. So Mr. Lay, is the voltage coming out here, is it going to be high or is it going to be low? High, yeah. And then this one's also disconnected, so it's going to be the same, I think, as before, right? Yeah. All right. So what that's showing us is that whatever values we have here, 1s or 0s, doesn't matter, because they're not attached to the bus. Okay. So if there is a conflict, like let's say that I think for one of these here we have a conflict, then sorry, not Z, it's going to be X. Okay. And so if there's going to be conflict, you have to write it's unknown, right, for the outputs. Okay. So the answer for the first one is 1x, 1x. Okay. So quick little worksheet that'll teach you how buses work. I think you guys can do it. Maybe. What if enable 4 and 5 are both 1? Then again, it's unknown. You put down x. The rule is you can only have one person transmitting, one person receiving. If you have 2 people transmitting, 2 people receiving, x. Who knows? Who knows what we'll get? Okay. Work time. If both outputs are connected, will they have the same output? No, x. You can have one person transmitting, one person receiving. Okay. All the answers are x's if you violate the one transmitter, one receiver rule. Okay. So we'll go ahead and put the that up on Canvas, and I will see you guys on Tuesday. So for Code Tennis, just get it done. It's not a hard assignment. It's just going to teach you about linking. You're just going to write a little essay, like a couple sentences. This is what I put into the thing. This is what I think my partner did, and the partner's going to do vice versa. This is what I'm doing to the thing. This is what I think my partner did. Don't talk to each other. Don't spoil it. It's part of the fun. Okay? So that is it for today, guys. I will see you on Tuesday as we're going to the finale of the semester. See you guys.